Let's talk a little bit more about databases and SQL. A lot of different things can be referred to as databases. So for example, if you've got a list of files on your computer, that's a database of files. If you look at the contacts on your phone, that's a database of contacts. What we're talking about in this course, though, is actually more than that. We're talking about database management systems, or DBMSs. And DBMSs can do a whole lot more than just storing and listing data. One thing DBMSs do very well is let you store and query very large amounts of data, terabytes of data, and they do so in a way that ensures that the data remains consistent and error-free. Databases also take care of concurrency for you, which means multiple people, or maybe processes or threads, trying to read and write data at the same time. Again, that can be something that's very tricky if you're just talking about plain text files. Databases also have ways to deal with user permissions and access. So if you only want some users to have access to certain tables, or some other users to only have access to a certain database, that's something you can do with a DBMS. You can typically also manage things like replication and backups, and they also often expose programmatic interfaces, which means that you can talk to the database using your favorite programming language, like Python or Java. So DBMSs, like Postgres, which we're using in this course, are far more than just containers of text files. And it's for this reason that your favorite website is most likely using a DBMS behind the scenes, rather than just storing all their user data in plain text files. In relational databases, data is stored in tables, which are also sometimes known as relations. And this is not too dissimilar really from, say, an Excel spreadsheet. But the data is stored in a way that has minimal redundancy and ensures that data integrity is maintained. The relational model requires that we break up our data into entities that are each stored in their own table, and we do this via a process known as normalization. This is fine and works well for a variety of different applications. There are other circumstances, however, where this presents a bit more of a problem, and this is where non-relational databases come into the mix. So for example, if you've broken your data that you wanted to store up into multiple different entities, which are each stored in multiple different tables, when it comes time to do some future reporting, you have to go through a process of rejoining all that data, sometimes called denormalizing your data. Depending on the size of your data, that can be a very expensive operation. Sometimes as well, it's just inconvenient to have to break up your data into multiple different tables and then constantly reassemble it. Sometimes that doesn't even make sense for the kind of data that you're trying to store. So non-relational databases grew out of a desire to address these problems. You'll sometimes also hear them referred to as NoSQL databases. And you might hear people talking about things like key value storage, or document storage, or graph databases. These are all types of non-relational databases. Incidentally, they're called NoSQL databases because more often than not, you don't actually use SQL to work with that database. Though more recently, SQL is becoming much more common even in the non-relational world. Often, you look to these more esoteric kind of databases when you have more specialized needs. But for most applications, almost everybody has a regular relational database humming away in the background. We can use relational databases for more than just storing and retrieving data. For example, we can ask databases to do all sorts of calculations internally before giving us the answer back. So if you have a database, for example, where you're storing the sales for your business, you can ask the database to sum over the full lifetime of your sales and tell you how much you've made, even if that consists of millions and millions of records. That's no problem for a database. We can also search through millions and millions of records for entries that are from a specific time range. Again, no problem. You can also do all sorts of interesting aggregations with a database. So you can use it to, for example, generate a report of sales by employee by month, rather than asking the database to return you all the records and then doing that sort of aggregation in an Excel spreadsheet. So databases enable you to do all sorts of rich and interesting data analysis. And this gives rise to people using databases for investigative analysis and data journalism. Okay, so we've covered the backstory. Now let's finally talk about what we came here to learn. SQL. SQL, or SQL, stands for Structured Query Language, and it's a programming language designed to query and manage data in relational databases. There are several categories of statements that make up SQL. So SQL can be used to create tables, to alter tables, and to delete tables. SQL can be used to work with the data within those tables. So you can use it to select, insert, update, or delete data that's within a table. And SQL also has a class of statements, which you can use to deal with granting and revoking security permissions. For this course, what we're going to focus on are the first two parts. So we're going to focus on the statements that are used to create, alter, and delete tables. And we're going to focus on querying the database and inserting and updating and deleting data. SQL is both ANSI and ISO standardized. It's a standard language, and there's a spec that's available online that you can get access to and read. It's also a non-procedural language. So to contrast that against a typical programming language that you might have used, like Java or Python or C++, those are all examples of what's called procedural languages. In those languages, there are branching statements, there's looping constructs, and in those languages, we write code that defines a sequence of steps that the computer then carries out and executes. With SQL, however, it's a non-procedural language. Sometimes it's also called a declarative language. And what we do with SQL is we define what we want the computer to give us. We define the inputs and we define the outputs. And we say, look, you take care of figuring out how to execute that. You look at the table structure, you look at my indices, you figure out what's the most appropriate execution path to give me what I want. And the component that does that is called an optimizer. And we'll talk about optimizers a little bit more in this course later on. So in this course, we're going to be using the Postgres dialect of SQL. What you find is that even though SQL is ANSI and ISO standardized, different database vendors have implemented their own dialects or their own variations of SQL. Most database vendors have done a pretty good job of following the standard. However, what you'll find is that some haven't implemented all of the standard, and in other areas, you'll also find that they've implemented even more than the standard. So different database vendors have implemented different keywords, new functionality, and additional things on top of SQL. Generally speaking though, we won't worry about that too much for this course. Everything that we learn in this course will apply to other databases as well. What you'll find is that there's some minor syntactic differences and some slight variations on what's possible. With some databases, there's faster and more efficient ways to do things, and with others, it won't work as fast. But the emphasis of this course is on concepts and problem solving. And so what you learn here, you will be able to apply regardless of whether you're working with SQL Server, MySQL, or any other database. Because SQL is a non-procedural language, that means that by default, it doesn't have some of those richer language features that you might expect if you've come from a background of working with Java, Python, etc. So out of the box, you won't find, for example, that you've got looping statements. However, depending on the particular database that you're working with, you might find that you come across PL SQL or T-SQL, which are non-standard SQL extensions with procedural elements. T-SQL is the language that you use when you're working with Microsoft SQL Server, where the T stands for transact. PL SQL stands for procedural language for SQL, and it's the language that you use when you're working with an Oracle database. These languages are more fully featured variations that include procedural programming aspects like local variables, loops, and control structures. We won't really be going into those things in this course because A, they're quite advanced, and B, it's very, very vendor specific. Additionally, while you can of course write more complex apps and scripts using these procedural additions, it's my recommendation that in general you'll be better served instead working with a traditional and richer programming language like Java or Python, and using that to execute simpler SQL statements from your code and maintain all your traditional logic there. This is the way, for example, most mobile, web, and desktop applications are built today. Okay, we've got one more little bit of theory to get through, talking a bit more about the relational model and how tables are structured and defined, and I'm going to introduce you as well to our sample database that we're going to be working through this course, and then we'll dive into writing some SQL. So in this video, I'm going to be talking about tables and the relational model, and I'm going to be doing it working in a tool called dbeaver, which is what you can see on the screen at the moment. So dbeaver is a database client. It's a database client that we can use to connect to our databases. We can write and execute SQL statements. And it's a tool that you're going to be using throughout this course as well. In a coming video, we'll walk through how to get your machine set up so that you can use dbeaver as well. There's lots of other database clients that are available. What I love about dbeaver is that it's free and it works on Mac, Windows, and Linux. And it's a very nice, powerful, simple to use client with a fairly intuitive interface as well. So in this video, we're also going to be taking our first look at our sample database that we're going to be using throughout this course. The sample database is called VideoEasy. And what this database represents is a fictional DVD rental company. The database holds information that you might expect a DVD rental company would have, like information about movies, information about the inventory that's available at different stores, their customers, their sales, etc. So our VideoEasy database consists of multiple tables, and a great way to get a sense of the different tables in your database and the relationships between those tables is to look at what's called an entity relationship diagram. So here we're looking at the entity relationship diagram for our VideoEasy database. We can see that there's all sorts of different tables, and the relationship diagram continues down to here as well. So what the diagram shows you is the different tables in our database, and it's got lines connecting the tables as well. These refer to the relationships between those tables, which I'll touch on in a little while. And it also shows you the different columns within those tables as well. So here we have the staff table, and you can see that there's a staff ID, a first name, last name, and so on. We apply what's called normalization rules to come up with a table design like this. I won't go into detail just now on how normalization rules work. It's a little bit beyond the scope of this course, but I'm going to point out now a few important aspects that will help you better understand these table designs, because that's important. You need to know that when you're writing SQL commands. So let's scroll down and let's have a look at the film actor, and the actor tables. And I'll jump over and have a look at the data that's contained within those tables. So we're back now looking at the film table. And one of the first rules of normalization is that each row or record in a table should be unique. And the way we do that is by defining a column or columns that uniquely identify each row in the table, and we call that column or columns the primary key. So let me explain that concept just a little bit more. If I say what is the column that uniquely identifies each row, what I mean by that is that there should be a column, and for each row of data, it should hold a value that uniquely identifies that row. Let's imagine that we tried to make release year our primary key. And we said, okay, give me the row with the year 2006. That doesn't work. You can see that there's lots of films that were released in 2006. So the release year data does not uniquely identify each row in the table. You could say, well, the title. Each movie has a unique title, right? And so maybe title would be a great candidate for our primary key. The problem is, however, that you may find that there are multiple movies with the same title. It could happen. What we often end up doing, therefore, is creating a new type of column which is guaranteed to be unique. In this case, that's called the film ID, and that's the primary key of this table. The film ID is just a number, and it's guaranteed to be unique for this table. Every single row will have its own unique number, which is basically auto-incrementing, going up by 1 every single time that we add a row to the table. It's called a surrogate key because it's something that we just made up, it's artificial, as opposed to being a natural key. Something like a title would be a natural key, but as we already discussed, multiple movies could have the same title, so it's not appropriate as a key. Often that column in the table is just identified by table name _ ID. So in this case, the table is the film table, and our column is called film _ ID. ID for identifier. Now let's have a look at our actor table. So our actor table has the columns actor ID, first name, last name, and just a timestamp column for when the row was last updated. The actor ID, as we've already now learned, is probably our primary key for this table. And this table contains a list of all the different actors that can appear in different movies. Let's jump back over to our entity relationship diagram. So we've shown the film table, and we've shown the actor table. What's interesting is that in this diagram, the column that we talked about as being the primary key appears up the top, and it's bolded. So in the film table, that's the film ID, and in the actor table, that's the actor ID. And that's how ERDs identify which column is the primary key of a table. So we've got a table that's storing films, we've got a table that's storing actors. How do we store what actors are in what films? This is where we use the film actor table. Let's have a look at the data in that table. So here's something that's quite interesting. You can see that the film actor table has got 3 columns, the actor ID, film ID, and the last update. So the first row says actor 1 appeared in film 1. Actor 1 also appears in film 23, actor 1 appears in film 25, and so on. So those numbers that are used there are actually the IDs of the actors and the IDs of the films in those other tables. So the actor ID here refers to the actor ID in the actors table. The film ID here refers to the film IDs in the film table. And that's what the entity relationship diagram was showing with those lines between the tables. Let's jump back over to the ERD. Notice here how there's a line joining film actor to film. Let's click on that line, and you can see that film ID is highlighted, and it says foreign key. So we've talked about primary keys, but we haven't talked about foreign keys yet. What a foreign key essentially does is maintain what's called referential integrity. So let's explain what foreign keys are looking at the film and film actor table. So you've got films, and films have IDs. And the film actor table describes what actors are in what films. So the film actor table has to refer to film IDs, but it has to refer to valid IDs. Let's say, for example, the film actor table said actor 1 was in film 263. But what if you went to the film table and there was no film 263? That would be invalid data. So what a foreign key does is it enforces the validity of that entry. So a foreign key defined on the film actor table for the film ID column says that you can only enter a film ID that appears in the film table. You can't enter in any other number. That's similarly the case with the film actor and the actor table. There's a foreign key defined on the film actor table, and it says you're only allowed to input actor IDs for valid actors. So you're only allowed to input IDs for actors that also appear in the actor table. And both primary keys and foreign keys are known as constraints. They restrict or constrain what kind of data you're allowed to put in a table, and they make sure that the data is valid. There's other kind of constraints that can be defined on tables as well. So there's primary keys, there's foreign keys. There's also things like a not null constraint. So you could do that, for example, with the film table and with the title column. If you don't want people to ever be able to input a title that's empty or null, then you put a not null constraint on that. And there's other different types of constraints as well, which we'll talk about later in the course. So why do we do normalization? Why go to all this work of breaking up the data that we want to store into multiple different tables, and then defining relationships between those tables, setting constraints, all these sorts of things? It feels like a lot of work, doesn't it? The reason why we do it is because, for one, it minimizes redundancy. Just imagine, for example, that we wanted to store films and we had a big film table. How would we store the actors for each film? What you could do maybe is have lots of columns on the film table. You could have a column called Actor 1, column called Actor 2, Actor 3, Actor 4, and so on. What that means though is that if you've got an actor that appears in lots of different films, that same actor is going to appear in the film table many times. The actor's first name, the actor's last name, etc. Just imagine what happens now though if the actor changes their name. What you would have to do is go through every single record in the film table and update the actor's name. You might miss some places, so there might be some places in the film table where the actor still has the old name instead of the new name, and it would be quite an annoying thing to do if the film table was very large as well. That's a lot of table updating to do. So through the process of normalization, we minimize the redundancy of data that's stored in our tables, and we ensure that the data remains consistent and error-free. At a high level, you can think of normalization as the process that helps us define the tables that we have and the structure of those tables, and you can think of constraints as being the thing that ensures that the right data is going into the tables. Both are key parts of the relational model. So now, when you come across your own database that you're working with, have a look at the tables, have a look at the entity relationship diagram, identify what are the primary keys, what are the foreign keys, and identify the relationships between those tables to help you understand how the data is stored. I should mention though that in relational databases, the data does not necessarily have to be stored in relational form. Sometimes you might just be working with a poorly designed database, and the database designer hasn't done a very good job normalizing the data. Sometimes you might find as well that the database designer has broken free of the normalization rules and implemented a slightly different design, maybe for performance reasons or for convenience reasons. So relational databases don't require that you store the data in this perfect normal form, but it's good practice. So what we're going to be doing next is we're going to get you to install Postgres. We're going to get you to install dbeaver, which is the tool that I'm using right now. You're going to create your first database and your first table, and then you're going to load this same sample database that I've been working with and talking about through this video. Let's install PostgreSQL for Windows. So what we first do is open up our browser and navigate to postgresql.org, as you can see it there. Once the page loads, let's go and click on download. We want to install for Windows, so let's click on Windows here, and then let's click download the installer. We're going to be installing the latest version of Postgres, which is 11.1, and we want to install for Windows, so let's pick the Windows x86 64 download. And the download should begin in the background. Okay, so once the download is finished, let's go to our downloads directory and double-click the installer. We're just going to be accepting the default settings for most of the installation steps, so let's go ahead and do that. Let's say next. The installation directory, let's leave as the default. And let's install all the components. There's a tool that we're also going to be installing called pgadmin 4, which is also a database client that you can use to connect to Postgres, and you can use that client to write and execute SQL statements. We're actually not going to be using pgadmin. As I mentioned earlier, we're going to be using a client called dbeaver, but pgadmin's another alternative you could use if you wanted to. pgadmin though still has a few quirks, and it's not necessarily as intuitive as using something like dbeaver. We'll install it anyway, just in case you want to have a look at it later on. We'll install to the default data directory. What you also have to do as part of the installation is provide a password for the database superuser, and that superuser's username is Postgres. You can type in any password you want here. Just make sure to write down the password and remember it, because we're going to use this later on when we're connecting to our database. And let's leave the port as the default as well. Let's leave the locale as the default. And we can review our installation settings here, but we've picked the default for pretty much everything, so let's just go ahead. Okay, Postgres is now installing. So at the end of the installation, you may get a prompt to launch Stack Builder, which we can use to download and install additional drivers. We don't need to do that though, so let's untick that and let's click Finish. Now let's download and install dbeaver. So in your web browser, navigate to dbeaver.io, and when the page loads, let's go and click on Download. We want to install the Community Edition, which is the free version of dbeaver, and we want to install this for Windows, so let's click on the Windows 64-bit installer. And the download will start in the background. Let's now install dbeaver. So let's go to the Downloads directory on our computer and double-click the dbeaver installer. So in terms of the components to install, let's leave the default settings as they are. So we want to install dbeaver and the JRE, which is short for Java Runtime Environment. Let's also tick the associate.sql files. And what that means is if we've got .sql files on our computer, if we're in Windows Explorer, we can double click on that file and it will open directly in dbeaver rather than, say, a text editor. Let's leave the install location as the default. And we're done. So we've now downloaded and installed Postgres, and we've now downloaded and installed dbeaver. In the next video, let's use dbeaver to connect to Postgres, and let's write a couple of basic SQL statements just to make sure everything's working correctly. Let's install PostgreSQL for Mac. So what we first do is open a web browser and navigate to postgresql.org, as you can see in the address bar there. Once the page loads, let's go and click on Download. Now let's scroll down and let's click on Mac OS. And we want to download the installer. What we're going to be doing is installing the latest version of Postgres, which is 11.1. So we'll go to Mac OS X and let's click the download button there. And your download should start in the background. Let's now go to our downloads directory and let's double click the Postgres DMG file that was just downloaded. And we'll double click on the install file. We want to open that. And because we're now installing a new program, let's enter in our Mac password. For most of the setup wizard, we're going to be going with the default settings. So let's click Next. We'll go with the default installation directory. And we'll install all the components. One interesting note is that one of the components is called pgadmin4, which is actually an alternative database client that you could use. Throughout this course, we're going to be using the database client dbeaver, which we're going to be installing just after this. If you wanted to, you could use pgadmin as well, but in my opinion, dbeaver is the richer and more intuitive database client, so we're going to be using that through this course. However, we'll still install pgadmin, so if you want to have a look at pgadmin later on, you're welcome to. We'll go with the default data directory. You'll also be prompted now to enter a password. This is going to be the password for the database superuser, and the database superuser has the username Postgres. You can enter any password in here that you want, but just make sure that you remember or write down the password that you enter, because you're going to need it later on when you connect your client to the database. We'll go with the default port, and we'll also go with the default locale. Okay, we can review the installation settings, but everything looks fine, so let's click Next. And we're now installing Postgres. Once the installation is complete, we'll be prompted if we want to launch a tool called Stack Builder, which is just a component that we installed that makes it easy to download and install some additional tools or drivers. We don't need to do that now though, so let's untick that and let's click Finish. So we're now going to be installing dbeaver, which is the database client that we're going to be using to connect to our Postgres database, and we're going to be writing our SQL statements inside dbeaver. dbeaver is a free and open source tool, and you can download it from dbeaver.io. So open up your web browser, navigate to that page, and once it loads, let's click the download button. And what we want to install is the Community Edition, which is the free version of dbeaver. So let's scroll down. For Mac OS X, we want to pick the package installer with the JRE, which stands for Java Runtime Environment. Click on that. And the download should start in the background. Once the download completes, let's go to our Downloads directory and run the installer. We'll hit Continue, Continue, Agree to the software license, Install. And because we're installing some new software on our computer, we have to enter the password for our Mac. And that's done. We've now installed dbeaver. Okay, so let's launch dbeaver and let's connect to our Postgres database. So what we do is go over here to the database navigator, right click here, and let's go Create New Connection. In Create New Connection, we'll just pick PostgreSQL. That's the type of database that we're connecting to. We'll hit Next. So what we're doing in this screen is we're setting up a connection to our Postgres database, which is actually running as a server on our computer. So our host is set as localhost. That refers to our computer. The port that the database server is running on is 5432, and that's the same port number that you would have seen when you were going through the installation steps for Postgres. So if you changed that from its default, make sure you enter in the right port number here. When we're setting up a connection to our server, we want to specify the default database that we're going to connect with. A database server can actually host many databases, and the default database that we want to connect to, at least initially for this video, has the name Postgres. It's a default database that just gets created for us. It's not one that we created ourselves. We're going to connect with the username Postgres. During the installation, I told you to enter in a password and then write down or remember the password for that superuser. So here is where we enter that password. What we'll now do is just click Test Connection. We just want to make sure that we can connect to our database correctly. And I got a success straight away. If this is your first time actually using dbeaver though, and trying to connect to your Postgres database, what you may get here is a prompt to install the appropriate drivers. If you do see this prompt, just click the download button. Once that completes, you should get a successful connection to your database. Let's click OK. And finally, under Settings, make sure that Show Non-Default Databases is ticked. Or if you're on a Mac, the setting might be called Show All Databases. Again, make sure that's ticked before proceeding. And now let's click Finish. After clicking finish, you may be prompted to create a sample database as well. It's not a bad idea to have this. We won't really be using it through this course, but it's something that's handy to play with later. So feel free to just click yes on that. And once you do that, you'll be over here and you'll be able to see in the database navigator, there's now that Postgres database that we're connected with. And there's also that sample dbeaver database. Okay, so let's bring up a SQL editor, which is where we're going to be writing our SQL commands. Let's go to SQL editor, SQL editor. So let me quickly explain a couple of things. So let's go over here, let's expand the database navigator. And what we can see is that we're using that connection that we just set up. So we're connected to our Postgres database with the user Postgres, that's our super user. And that server is currently hosting one database, and that database has the name Postgres. We can expand that database, and we can expand schemas and the public schema, which I'll explain just in a moment as well. And we can see that there's tables, views, materialized views, and other objects. Let's expand tables. There's nothing in there. So this is an empty database with no tables. Earlier, I mentioned that databases contain tables. However, tables actually live within something called schemas. So a database contains schemas, and schemas contain tables. So you can think of a schema as basically a container of tables, views, stored procedures, functions, etc. Basically, everything that you see here listed under the public schema. What we want to do whenever we're working in our SQL editor is always make sure that we're targeting the right database and we're targeting the right schema. And we can see what our active database and active schema is here in the toolbar. Let's make sure that we're targeting our Postgres database. So let's select that. And then let's make sure that our active schema is the public schema and the Postgres database, which it is. So that's correct. What that means now is that any SQL statements that we write and that we execute will be run against the Postgres database, which is what we want. So rather than working with this Postgres database though, let's create our own database. Let's write create database and let's call it myfirstdb. What we want to do now is execute that SQL statement. And the way we do it is by going over here to this sidebar and clicking on Execute SQL Statement, or if you're on Windows, you can also press Control-Enter on your keyboard. We're executing that statement, and we've just created our first database. If we want to see that database, let's go over here to the Database Navigator, let's click on our connection, we'll right-click on it, and we'll click Refresh. And there it is. There's our database that we just created. And we can expand that database, and we can see that it also has a public schema. By default, whenever you create a new Postgres database, it's going to come with a public schema. What we want to do now is we want to create a table within that database, and we want to put some data inside that table as well. So we want to write SQL statements, and when we run those SQL statements, we want to run those against that database that we just created. So let's go over to the Database Navigator, let's right-click on the database that we just created, and let's select Set Active. Notice that when we did this, that the toolbar changed. Now it says public, so that's the public schema, at myfirstdb, which is the database that we just created. So it's still the same Postgres database instance that we're connected to, but we're just now connected to a different database, the myfirstdb database. So we've created the database. Let's go down now, and now let's create a table within that database. So let's type create table. Let's call it employees. Within that table, we're going to have 4 columns. Our first column is going to be called employee ID, and it's going to be of type int or integer. We're going to store the employee's first name, and that's going to be of type varchar 100. What that means is that the first name is text up to length 100. It's a variable length character array. We're going to store a last name, also going to be a varchar of length 100, and we're also going to store a hire date of type date. Let's move this down a little bit out of the way to give us some more working room, and we'll put a semicolon at the end of that statement. You should always end all SQL statements with semicolons. Now, something worth pointing out here is that what we want to do is we just want to execute this statement, this create table employees statement. We do not want to execute this statement again. We've already created the database, it's unnecessary. And that's going to be the typical way that we work throughout this course, and in general, just when you're working with databases. You often just want to execute one statement at a time. Our cursor right now is just on this create table employees statement. It's down here at the bottom. If we were to now go up and click execute SQL statement, what will happen is that we would only execute this statement. We would not be executing the create database statement. And that's exactly what we want. You can kind of think of this as like the way that you work with a command line, or if you've worked with something like Jupyter Notebooks or IPython before. What we're going to be doing is typically just executing one statement at a time. If we wanted to execute the whole script, so if we wanted to execute both the create database statement and the create table statement, what we could do is go over here to the sidebar and we would click execute script. Throughout this course, I'm pretty much exclusively just going to be using the execute SQL statement command. If I ever want you to execute the script, I'll let you know. So let's just execute this statement, this create table statement. If you want to see that table, come over here to the database navigator, My First DB, public schema, tables, and we may need to hit refresh. And there it is. There's the employees table that we just created. Let's insert some data into that table. So let's insert in an employee ID 1. Let's use the first name John, last name Smith, and the hire date as 2010, July the 1st. And we could, let's insert, let's say just 2 records. So insert an employee ID of 2. This time we'll insert Peter Jones, and let's do a hire date of 2008, 1st of January. What I've now typed up here is a SQL statement to insert some data into that table. If you're following along, don't worry too much about the actual SQL statements that I'm writing. Later on in this course, I'm going to come back and explain these in more detail. The idea here is just to get comfortable typing in SQL statements into dbeaver, executing them against our database. So what I'm now going to do is execute that statement. And we can see down the bottom in our statistics, it says updated rows 2. So we've created this table of employees. We've inserted 2 people into that table. Now let's ensure that that worked correctly by just selecting from that table and making sure the records are in there. So we'll go to our editor, and what we'll type in this time is select star from employees. And we'll execute that statement. And throughout this course, I'm just going to be using keyboard shortcuts. So when I say let's execute that statement, I'm just going to be pressing Control Enter, or if you're on a Mac, the keyboard shortcut might be a little bit different. And there we are. We can see that there were 2 employees that we were able to successfully insert into our table. I mentioned earlier that we're working within the public schema, and so that's our namespace. What that means also is that if you want, you can refer to tables by a more fully qualified name. So while you can also just write select star from employees, and because we're connected to our public schema that works, You can also type in public.employees, and we can execute that, and it works just the same as well. So that's just a more fully qualified name to refer to your table by. Just retouching on the idea of schemas, what you may sometimes find in big databases is that there's multiple different schemas. So you may find that if you have a very, very big database with, say, like hundreds and hundreds of tables, that there's lots of different schemas that help organize those tables. And that provides some cleaner logical grouping and logical separation between tables. Right now, we don't really need that. We're just working with one table, so we're just working within the default public schema. So there's a couple of important things I should point out. The first is that SQL is case insensitive. So what that means is that you'll often find people writing those keywords like insert into and select in uppercase. In fact, that's quite common. Personally, I prefer using lowercase because I think it's just easier on typing. You basically just want to find your own style that works best for you. Similarly, there's no well-defined naming conventions that everybody agrees on for how to name tables or how to name attributes. Personally, I like to use the pluralized version of a noun for table names, so I called my table here employees, and my column names are all lowercase, and I use underscore to separate words. So I have employee underscore ID, first underscore name, last underscore name, and so on. Again, this is an area where people have different conventions. I think the main thing really though is just to be consistent within the code base that you're working with. When you're working in SQL, you can write comments into your code as well. So if we go down here, if we just wanted to write a comment that wasn't executed, what we do is use 2 dashes as follows, and this is a comment. So what that means is that if you were to execute the script, or if you tried to execute this as a SQL statement, nothing would happen. It's essentially ignored. And we leave comments in code just for our own benefit so that we can read them later on and remember what we were doing, or for the benefit of other developers who are working with our scripts. Let me quickly show you what an error looks like as well. So if you make a mistake while you're typing some SQL statements, let's have a look what that looks like. So let's say we did select star from, and we wrote employee with 1 E, and we tried to execute that statement. We get an error, and it says the relation employee does not exist. So throughout this course, as you're writing SQL commands and executing them, when you get errors like this, read the error description and try to figure out what you may have done wrong. Often it's going to be something simple, like you mistyped the name of a table or an attribute, or you forgot a comma somewhere. It's usually pretty simple to work out. Often what's helpful as well is just to take that error that you got, put it into Google, and have a read of some of the answers that people give. So we'll say OK on that. We'll fix up that query. We'll run that again, and now it works fine. So we created our first database. We created a table within that database, and we created that table within the default public schema. We inserted some data into that table, and then we wrote a query on that table to get the data out of it. That's really all we wanted to accomplish with this video, to get some familiarity with dbeaver. If we're done, we can now clean up. So what we can do is we can type in drop table employees, and we want to execute that. And what that did is delete that table. Let's go over here to our database navigator. Let's click on tables and let's refresh that. And our employees table is gone. You'll often find when you make changes like this, like creating a new table or deleting a table, you'll have to come over here to the database navigator and you'll have to refresh the parent just to make sure that that gets updated and is reflected in the view. So we're done with my first DB. If we want, we can just delete that database. If we try to go over here though, and we right click on the database and we click delete, we'll say yes. We'll get a warning that we can't delete that database because we're connected to it. It's the database that's currently active. So what we want to do is let's just hit OK on that. Let's go over here to our database navigator and let's change the active database. So let's right click on Postgres, that's the default database, let's click Set Active. And so that's bolded. That means that's our active database. And so now we can go back, we can right click on My First DB and we can click Delete. And that database is gone. And you'll see reflected up here in the toolbar as well. Obviously the connection has remained unchanged. We're still connected to the same database server, but now our editor is connected to the public schema on the Postgres database. So if we were to write a SQL statement here, if we were to try to create a table, that would all happen on the Postgres database inside the public schema. So this has been a quick overview of dbeaver and just writing some basic SQL commands. I'm going to come back later in future videos and you'll get very intimately familiar with all of these different SQL commands that we wrote. But the goal here was just to play around with dbeaver, spend some time in it, get familiar with connections, get familiar with databases and creating tables. What I'd recommend that you do after watching this video is spend a little bit of time inside dbeaver. If you want, you can create some more databases and you can practice creating some tables within the database. Get familiar with using the execute SQL statement command, and if you want, try out executing a script as well. So write several SQL statements in a row and then execute script, and you'll see that it will execute all of those statements rather than just the current statement. If you want, you can also try out using execute SQL statement in a new tab, and you can also try out using execute the script with all of the results appearing in their own tabs. In the next video, what you're going to be doing is taking a script and using that to create the sample database that we're going to be working with for the remainder of this course. Before we proceed further, I wanted to show you several tweaks and changes that you can make to dbeaver to improve your overall experience going forward. First, let's look at changing the font size. Go up to Window, Preferences, and in the search bar, type in Font. Select Colors and Fonts, and you'll find that you'll be taken to this dialog. Expand Basic, scroll down, and select Text Font. If you now click Edit, you can change the font size of the text in your editor. I've got my font size set to something quite big right now, 24, just for recording purposes. Play around with the different fonts and font sizes and choose something that's comfortable for you. In particular, you'll find that if you're on a Mac, by default the font size is quite small, so you likely want to increase it. The next preference that we may want to change is changing the tab width. Right now, it's set to 4 spaces. And you may also want to change the editor to use spaces instead of the tab character. So up in the search bar again, search for tab, and under General Editors Text Editor, we can tick Insert Spaces for tabs, and change the tab width from 4 to 2. If you hit Apply and Close, that takes effect immediately. Obviously, you're welcome to keep tabs instead of spaces if you prefer that, and to set your tab width to whatever you like. Spaces instead of tabs, and 2 spaces is my preferred preference though. You may have noticed as well that autocomplete suggestions are offered as you type. For example, if I'm writing a create table statement, notice how it was popping up suggestions as I was typing. In my opinion though, these are not particularly useful, so I like to turn these off. If you want to do that as well, go to Window, Preferences, search for Completion, and under SQL Completion, I untick all 3 of these options. Apply and close, and now you'll see as I type, I don't get suggestions. Do note though that even after turning these off, you can still get autocomplete suggestions if you want. You just have to press Control Space as you're typing to get them. For example, I can start typing create, Control Space, and now I'll get that autocomplete suggestion again. In my opinion, that's less annoying than getting prompts all the time, but it's up to you. Feel free to leave these on if you want. There are a couple of changes I also like to make to data formatting. So in Window, Preferences, search for Data Format. And in this dialog, I like to change the number format to turn off grouping. And you notice below that there's a sample value to demonstrate what the change would look like. So when we turn off grouping, it removes the commas. For me, this is preferable because often the numbers that you're displaying in your results windows might be, for example, the year or something like that, where it doesn't really make sense to have grouping. I also like to turn off Use Data Type Scale for fraction digits, which in dbeaver tends to result in fractional numbers having too many digits after the decimal point, and it can look a little bit strange. You may notice as well that when I'm working in the editor primarily, I like to minimize the database navigator so it's not in the way. For example, right now it's minimized. If I bring it back, I can click over here on the database navigator, I can select Restore, and likewise for the project view, I can restore that as well. If you like the minimized view like me, then just come up here and select the minimize option for both the project view and the database navigator view. And once you've done this, you can just bring them back as needed and then click out when you're finished. dbeaver also supports theming, and in particular, it has a dark theme. To enable that, go to Window, Preferences, search for Theme, and click on the Appearance button. My theme is currently set to light. We could change that to dark and hit Apply and Close. Okay, so hopefully these tips help improve your dbeaver experience for the coming videos. In this video, we're going to be setting up the sample database that we're going to be using throughout the rest of this course. So what you first need to do is go to the GitHub link in the description for this video and make sure you download the Video Easy setup file that's there. Once you've downloaded that file, open up dbeaver, and the first thing that we're going to be doing is just writing a single statement to create the database, and then our script is going to be populating that database with tables and data. So let's create the database. We can execute that statement. Let's head over to the database navigator and make sure that it was created correctly. We'll have to refresh. And we can see there's our Video Easy database. Let's now set that as the active database. Okay, so that's our active database. And what that means is that any scripts or any SQL statements that we run now will be run against that database, which is what we want. Now let's open that script that we just downloaded. And we'll just bring our results tab down a little bit. Okay, so this script contains some statements that you wouldn't be familiar with at this point. However, if you scroll down a little bit further, what you'll find is that it does create statements that you would have seen in the previous video. So you can see this script has statements like creating a table called customer. You can see that they're creating a table called actor. And if we scroll even further down, you can start to see some insert statements where data is being inserted into those tables that were just created. So what we want to do now is we want to execute the whole script. We don't want to go through and execute one statement at a time. This is a very big file. We want to execute all of the statements in this file. So firstly, let's just double check once again that Video Easy is our active database. It's bolded. And you can see up here in the toolbar as well that the Video Easy database is the active database. Okay, so that looks good. So we're going to come over here and click Execute Script. Now this is a big script. It contains a lot of insert statements. There's a lot of data that's getting inserted. So it will probably take a couple of minutes on your computer for this script to run to completion. You can track the progress in the bottom right corner. Okay, so once that script has completed successfully, we'll find we'll have a whole bunch of different result tabs. We don't need those, we can get rid of those. So let's go close multiple results and get rid of those. Now let's go and have a look at the entity relationship diagram for this database. So we go over to the database navigator. And on the public schema, let's right click and we'll select View Diagram. And I'll zoom this in to 150%. And what we're looking at now is the relationship diagram that we saw as well in the earlier video. So we can see that it's got our tables represented in the diagram, and the lines joining the tables representing the relationships between those tables. So that's good. It looks like our database schema was created successfully. Now let's have a quick check and make sure that all our data was inserted correctly. So we'll close this. We can close the script now as well. We no longer need that. And we can get rid of this create database statement. So we're just working in a blank SQL editor again. And we know that there's a table called film. Now let's just select all the rows from the film table. So that's great, that works successfully. We can see that there's a bunch of different films in our film table. So it looks like all the data was inserted in our tables correctly. We can check some other tables as well, so we can have a look at the actor table. We can execute that statement. That looks fine as well. Okay, so finally what we might do is just a little convenience thing for ourselves, so that whenever we open dbeaver in the future, we'll be automatically connected to our VideoEasy database and ready to write statements against that database. Right now, if we were to close dbeaver and reopen it again, we would be connected to the Postgres database by default. So we can change that really easily just by going over to the database navigator, right-clicking on our connection and going Edit Connection. In this dialog, we can see that our default database that we connect to is Postgres. Let's just change that to VideoEasy. And we can hit Test Connection, and that works fine. So let's hit OK now. We'll get prompted to reconnect, and let's just press yes. And we don't want to save the script, so we can just hit no. Okay, so now whenever we open dbeaver, we'll be automatically connected to the VideoEasy database. And we can see that that's our active database. Maybe let's rename this connection just so it's got the correct name. So change that to VideoEasy. And that's done. Okay, so that's fantastic. We've got our sample database set up, and we'll be using this sample database throughout the rest of this course. Now, it's time to dive into some SQL. In this video, we're going to be looking at the select statement. The select statement is at the heart of most SQL querying. Let's jump in though and take a look at a simple example where we're querying the database for all of the columns and all of the rows from a particular table. So let's pick the customer table, and let's look at the following statement. And we can execute that. So what we've done here is we've said select star from customer. What the star means is select every column from the customer table. And there's no other conditions with this query, so we've also selected every row from this table. If instead we just wanted to pick some particular columns that we wanted to query, so let's say we just wanted to get the email address and not all these other columns, what we could do is go up and change the query, and we can execute that. And now we've just selected the email column only. What if we wanted to select multiple columns? What we had to do here was just put a comma in between every column that we wanted to select. So let's say that we wanted to add email back in as well. We can do that just by typing comma, email. And so what we've done here is we've selected the first name, last name, and email address of every single customer in the customer table. It's important to note that with these select statements, when we're doing querying against the database, that it's actually just a read-only operation. We're not modifying the database in any way. There's no risk that we're writing new records to the database. It's just a pure read-only select where we're asking the database to give us information from its different tables. You might find it handy to have open while you're working with your database the entity relationship diagram. We can pull that up by going over to the database navigator. And let's make sure that we're looking at the VideoEasy database, and we go to the public schema, and what you can do is right-click on that and go View Diagram. And I'll bring that up to 150%. While you're working throughout this course, and just in general when you're working with the database, it's often very handy to have the ERD open just in the background. So throughout the coming videos, I'm going to leave this open just in a tab here up the top, and I'll be referring to it quite often. So I'll be jumping back and forward between the editor and the ERD, just so I can refer to table names and column names. Something to point out as well is that we just wrote select first name, last name, email from customer. And I told you that that has selected all of the rows from that customer table. However, what you'll find is if you have a look down here in the output area, it says 200 rows fetched. However, I happen to know for a fact that the customer table has much more than 200 rows. So what happened? What you'll find is that when you're working with database clients like dbeaver or many others, they often will by default fetch a fixed number of records from your table just in order to save bandwidth and improve performance. Say that your database that you're connecting to is on a server, and that server is in a different country, for example. It could be a very expensive and slow operation if your table has 1 million rows and you did a full select statement on that table, and your client then had to handle fetching and displaying 1 million records. dbeaver by default will only fetch 200 records at a time, and so that's why it says 200 rows were fetched. Let's change that, because throughout this course, what we're doing is just working with a local database that's on our machine, and we're not working with any particularly big tables as well. So there's no performance difference for us with selecting 200 rows versus selecting 10,000 rows. Let's go up here, and you can see that there's this maximum result set size option. Let's change that from 200 to 20,000 and hit enter. Now, whenever you perform a select statement from a table in your database, it's going to return up to 20,000 rows at a time, and that's fine for us. With our sample database, we actually don't have any tables with more than 20,000 rows. Now, what if we wanted to change the column names in the output? Right now, the name that appears in the output is just the column name that you selected. We can do something called aliasing to rename columns to something a little bit nicer. So let's say that instead of having first underscore name as our output column name, we just wanted it to be first name. Let's go in and change that. And we can execute that. And now you can see the column has the name first name, which is what we wanted. So we can use this as statement if we want to clean up our column names a little bit. Sometimes you might actually see people leave off the as statement. So it is actually valid SQL to just leave off the as part and write it as follows. And we can execute that, and it will run just the same. However, I find this a little bit unclear, it can become a little bit confusing, and it can cause you some other problems down the road as well. So whenever you're doing aliasing, always put in the as part, just to make things very clear. Did you notice now as well that since we changed the maximum result set size to 20,000 rows, when we ran this query, we actually got 599 rows fetched. And you can see that in the output window there, where previously we were just getting 200. So that was the effect of changing that maximum result set size. Our customer table actually has 599 rows. Lastly, something that you'll find is quite convenient when you're working in the editor is to actually type the table name first and then to go in and add your select columns afterwards. And I'll show you why. So let's say that we wanted to select some columns from the actor table. So let's delete this. Let's get rid of this. Let me type in select, and now I'll go from actor. And I'll put the semicolon in there as well. Because I've typed the table name first, what I can now do is go up to the select line, and I can, on Windows, hit Control Space. And what that's going to do is bring up some autocomplete options, and the autocomplete options are going to be column names from this table. So the actor table has an actor ID, first name, and a last update column. This was only possible because I put in the table name first. So I can now just go first name, last name. And I didn't have to type it, and I didn't risk making any typos when typing out the column names. And I can execute that, and that runs fine. So that's quite convenient. If instead I had just started out with a blank slate and I'd gone select and I press Control Space to get suggestions, I would have no suggestions at all. Because I haven't typed in the table name yet, dbeaver can't offer me any options. It doesn't know what table I'm going to be selecting from. So this is why when you're working in dbeaver, it's often really handy to start by writing an empty select statement, go down, type your from statement, pick the table that you're working with, and then go back up and make use of autocomplete just to avoid any typos. Okay, so you've seen select star as a wildcard to select all of the columns from a table, and you've seen selecting one column and selecting multiple columns from a table as well. Go ahead and give it a try in the exercises to follow. In this video, we're going to look at what are called derived or computed columns. So far, we've looked at select statements where we picked the particular column that we wanted in the output. However, what if we wanted a column in our output that was the result of a particular expression? Let me make this a little bit more concrete with an example. So let's have a look at the film table. And we always end our statements with a semicolon. So we can see that here in the output, if we scroll along a little bit, there's a column called rental duration. And this appears to be, for each film, the number of days that this film can be rented. What if we wanted to, in our output, for example, select the rental duration in hours, not days? How would we do this? Well, we would need to write some sort of expression, something that takes that column and then modifies it. And we can do this in a fairly intuitive way with SQL. So we've done select rental duration times 24, because there's 24 hours in the day, and we'll actually go back in and we'll select the title as well. So let's execute that. Okay, so that appears to have done what we wanted. We can put back in the original rental duration if we want, just to compare and double check. So this new column that's added to the end now, this rental duration in hours, is what's called a computed column. You'll notice as well that the column actually doesn't have a name at the moment. It's got this question mark column question mark. And this is where we'll use aliasing that we learned in our previous video to give it a nice friendly name. And we can execute that. So with SQL, you can use the full range of operators that you'd expect depending on the type. So if you wanted, you could do addition, subtraction, multiplication. Depending on the type, you get all the standard operators that you'd expect. We can also use parentheses just to manage the order of operations and to make things a little bit more clear. So I'll break this out so everything's on its own line. Now let's say we just wanted to introduce parentheses just to show off order of operations. What we could do is put parentheses here around rental duration times 24, and we'll just do +1. Run that. We're not really doing anything meaningful here. I'm just demonstrating that you can use parentheses to control the order in which things happen. So here we do rental duration times 24, and then we add 1 to that result. What's interesting about SQL is that you actually don't even have to use columns necessarily. You can kind of use SQL like a calculator. So let me demonstrate that. And I can execute that. So that's quite interesting, isn't it? I can just put my own expressions in the select statement, and I didn't even have to refer to any column. I didn't even have to refer to any table. So if you just want to play around and explore using different types of expressions in SQL to calculate columns or to calculate results, you can do that in this way. You can actually also create in your output entirely new columns by combining existing columns together. So as an example of that, let's first just clear this off. We'll get rid of that. Let's go and have a look at our entity relationship diagram, and let's look at the rental table. So here's our rental table, and this describes when different films were rented out and when they were returned. And we can see that there's a rental date and there's a return date for each film. So let's have a look at that with a query. And we can execute that. Now what if we wanted to add a new column to our output, which shows how long each film was actually rented for? So the return date minus the rental date. Well, we can do that, and again, it's fairly intuitive. You can perform these types of arithmetic operations on dates as well. So we can go up here and we can go return date minus rental date, and we can execute that. Again, notice how the column doesn't have a well-defined name, so let's give that a nice name. There we are. So you can create your own new column, which was the result of combining other columns together in an expression. Here, we've subtracted one date from another, but you can also do other types of date arithmetic. So you can also add dates together, for example. We've looked at expressions involving numbers, and now we've had a quick look at an expression involving dates. However, what if we wanted to combine text or strings? Let's do that by looking at the customer table. Firstly, let's just pull up the columns from the customer table and let's see what we're working with. So we'll clear this off. Okay, so we can see that in the customer table, the first name and the last name of each customer are stored in their own columns. What if we wanted to create some sort of new column in our output, which is just the person's full name? So first name, space, last name. So let's firstly just grab the columns that we actually do want. So let's select the first name. Let's select the last name. And let's just run that as is. So what we want to do now is find a way to add a new column, which is the combination of the first name and the last name. And the way we can do that with SQL is by using this pipe character twice. That's called the concatenation operator, and it will allow you to join text together. So let's give it a go. Type first name, concatenation operator, space, concatenation operator, last name, and we'll use aliasing to give the column a name like full name, and we can execute that. And there we are. We've created a whole new column, which is the combination of the first name and the last name. And we did it with the concatenation operator, which joined first name with a blank space with last name. So there's something else that's bugging me though, and that's that the names are all in uppercase. What I really actually want is a column called full name, but I want the name to be capitalized correctly. So I want Mary Smith to have a capital M, a capital S, and every other character to be lowercase. To do this, I'm going to introduce something called functions. SQL comes with a range of functions that are useful for transforming different kinds of input into different kinds of output. What I'm interested in initially right now is string functions, functions that act on strings to modify them in some way. So what I can do is I can open up the Postgres documentation. To have a look at the documentation, navigate to postgresql.org, and when that loads, click on Documentation. And let's look at the online manual for version 11 of Postgres, which is what we installed. So what we want to do is search the documentation for string functions. And we can see that this result here looks like what we're after, string functions and operators. So let's click on that. Okay. So we can scroll down and we can see some interesting functions that are available for us to use. You'll notice that you can see this double pipe operator, which is what we just used now. So this says string concatenation, and it's for combining two strings, and they give an example of that as well. We just made use of that. So here's one that's interesting. There's apparently a function called lower, and it says it converts a string to lowercase. Let's try and use this lower function in our code, and let's see if it does what we wanted to do, because our problem is that our customer names are all in uppercase. So back in dbeaver now, let's use this lower function and see if it does what we want. And let's execute that. Okay, that's interesting. So now we have a column called full name, and all of the names are in lowercase, which is what lower said it would do. Lower converts the input, which is the combined name, so this is the input, first name concatenated with last name, and it converted that to fully lowercase. That's close to what we wanted, but it's not exactly what we wanted. What we actually wanted was the full names to be capitalized correctly, so lower is not the function we want. Let's head back to the documentation and let's see if we can find a function that does what we want. Let's scroll down a little bit more. None of these functions look like what we want. There's some quite interesting ones here. We'll revisit these a little bit later and we'll explore what they do for us. Oh, here's an interesting function, initCap. And it says it converts the first letter of each word to uppercase and the rest to lowercase. And they give an example of using it as well. This kind of looks like what we want. Let's give it a go. So we'll replace lower with initCap. We'll execute that. Perfect. That's exactly what we wanted. In later videos, we're going to spend quite a bit of time getting familiar with the different functions that are available to you. There are hundreds and hundreds of different functions that are available for you to use. Some of them work with strings, some of them work with dates, some of them work with numbers. What I'd recommend you do is bookmark that documentation page. And throughout this course, you'll find yourself going back there and referring to it and just looking up functions as you might need them. It's a good idea to just go and explore and familiarize yourself with it. The idea isn't to memorize all of the different functions that are available to you, but just to be broadly familiar with the types of functions. And later on in this course as well, I'll be going through some videos where we look at some of the most common functions. So this was just a quick introduction to derived or computed columns. We looked at how we could create expressions and different ways that we could combine columns together as well. Finally, we had a quick look at using functions in those expressions. So far, with the queries that we've been writing, we've been returning all the rows in each table. However, what if we wanted to filter the rows that are returned so that only those that meet a particular condition are returned in the output? We can use the SQL where clause to do this. Let's start off with a simple example where we want to filter some of the rows in the film table. So firstly, let's just look at the film table again. And we can see that with the rental duration that the data type of that column is a number. It's got this 1, 2, 3 icon in the corner. And that makes sense because the rental duration is a number. It's just the number of days that this film can be rented out. So what if we just wanted to write a query to get all the films that have a rental duration of 5 days? Let's go and do that. And now we're going to introduce our new where clause. And we can execute that. Okay, and that appears to have worked. We got 191 rows returned, and all of those films have a rental duration of 5. Here we use the equals symbol to check for equality, but we can use all sorts of other comparison operators. So I'll write a comment now just listing out all the different comparison operators that are available to us. So we can use equals, which we just used now. We can do less than, we can do greater than, we can do less than or equal to, we can do greater than or equal to, and we can also do not equal to. And there's two different ways that you can do this. You can do this, or you could write it as this. This greater than, less than way is actually the standard way to do it, and this is the non-standard way, but it's actually very commonly supported across a wide variety of database engines, so often you can just use that as well. So let's give some of these different comparison operators a test spin. So we've already used equals to look for when the rental duration is 5. What if we wanted to see films where the rental duration was greater than 5 days? We would replace this, and we can run that. And we've got 403 rows returned, and all of those films have a rental duration of greater than 5. What if we wanted to do less than? And that appears to have worked. If we scroll the output, we can see they're all less than 5. And what if we wanted to do not equal to 5? And again, if we scroll our output, that appears to have worked. What if instead now we wanted to filter on a column in a table which is a text or string data type? Let's go and have a look at our customer table. So let's clear this query off, and now let's just have a look at the customer table. And we can execute that. And we can see that there are columns first name and last name, and they appear to be text. By the way, we'll be talking about data types in a little bit more detail coming up. This is just a quick first look at them and how to query against them. What if we now wanted to return all the customers with the first name of Mary? Again, we can use all those same types of comparison operators that we have in the comments there. So let's just try using equals. We didn't get any results. Why is that? When you're comparing using a text data type, it's actually going to be case sensitive. So in this situation, there are no customers with the first name Mary in lowercase, but there is a customer with the first name Mary in uppercase. So we can run that, and now we have our match. So just remember when you're doing comparisons with text data types that it is case sensitive. And coming up, I will show you some more powerful text filtering and searching techniques that will allow you to deal with uppercase or lowercase. Notice here as well that we used single quotation marks around this text. So when you're writing in string literals in SQL, you use single quotes. And don't get that confused with double quotes, which you only use for column or table identifiers, like we saw when we were doing column aliasing. You can also use all the other comparison operators on text, just like you did with numbers previously. So if you wanted to see all of the customers with a first name that's not Mary, you could just change that to not equal to, and we could run that. And we can also use greater than or less than operators. And there it's going to use dictionary alphabetic ordering to do the comparison. Incidentally, just going back to that first example where we were looking for customers with the first name Mary, if you weren't sure whether the first name was stored as uppercase or lowercase, you actually already know one technique that you could do to handle that. What you could do is use the function that you already learned about, lower, and run that. So your where clause can contain expressions as well. You can use all these same types of comparison operators against dates and times as well. So let's just go and have a look at the rental table first. And we're already pretty familiar with the rental table by now, but we know that there's a column called rental date, and that rental date column is a date time type. In Postgres, that's actually referred to as a timestamp. So you can come down here and hover over this clock icon, and you can see that it says timestamp. And what that means is that this column stores dates and times. Something that's quite handy in dbeaver, if you're ever curious about the different types of your columns, is you can go over to your ERD, and what you can do is you can right-click anywhere in the background, go to View Styles, and go Show Data Types. And what that will show you then is next to every column, the different data type that's being used. A lot of these won't be familiar to you just yet. There's a video coming up where we're going to walk through the different data types in a bit more detail, but this is a useful view to have on all the time. Okay, so we were looking at the rental table, and let's say that we wanted to only return rentals that were made in 2006. How would we do that? Well, we could make use of this new where clause, and what we can do is say where rental date greater than or equal to 2006 1st of January, and we can execute that, and we can see that it's only returned rentals from 2006. Did you notice here how we had to write the date in single quotes, and we also used this format year-month-day. What's actually happening behind the scenes is you used single quotes, so this is a text literal, and then that text literal was converted or casted to a date. for the purposes of comparison with the rental date. You always want to use a date format that's unambiguous. So in this case, year, month, day is unambiguous. That's an ISO standard way to write a date. If instead you tried to do month, day, year, or day, month, year, you could get unexpected results when it does that conversion of that text literal to a date. So always use year, month, date as I've written it here. One final thing I want to point out, when using the equal sign with dates, let me just reset things back to showing all of the rows. We can see that there was a rental made on the 24th of May 2005. So what if we wanted to filter on that and return that? We want to see all rentals that were made on the 24th of May 2005. You may try and do this initially. Okay, and you would think if you run this that you might get all of those rentals that were made on that day. Let's give it a go. But we didn't get any results, so what happened here? What happened is that rental date is actually storing a timestamp that contains both a date and a time. So when you use the equals symbol here, it was looking for an exact match not only on that date, but also that time. So again, let's just comment this out for a second, this where part of the clause. Let's come up here, let's rerun this query, which is just select star from rental. And we can see that what the actual value is of the rental date column is the 24th of May 2005, 10:54 p.m. and 33 seconds. So if we want to use the equal sign to perform a match, we would actually have to enter in that exact value. So let's go and do that now. We can uncomment that. Let's come in here, let's write 22, 54, 33, and now we can run that. And now we've got our exact match. And we can use all the other comparison operators as well. So if you want to use not equal to, we can do that. If you want to use greater than, we can do that. And all those standard comparison operators apply and work just the same on dates as they do on numbers and text. This was a quick look at the where clause in select statements and how you can use the where clause to filter the returned rows in your table against all the different kinds of data types. Have a go at these in the exercises, and then in the next video we'll look at combining logical expressions with and or. We can use the and or keywords to combine logical expressions in our where clause. So to start out now, we're just looking at a simple query where we're pulling down all of the rows from the film table. Let's filter that so that we're just looking at films where the length is greater than 100. And we can run that. And now let's also make it so that we're filtering for films where the length is greater than 100 and the rental duration is 5. We can use the and keyword here. And we can run that. And there we go. Let's scroll our output a little bit. We can see that all of the films that got returned have a rental duration of 5 and a length greater than 100. What if we wanted to see films where the length was greater than 100 or the rental duration was 5? Either could be true. Let's change the and to or. And run that. What we can see now is that we've got films in our output, like African Egg, which has a rental duration of 6 and a length of 130. So the length condition matched, but the duration didn't, and that's fine. When you use or, only one of the two conditions has to match, whereas with and, both of the conditions have to match. We can use and or as much as we want in the where clause. So this time let's change it so that we're looking for films where the length is greater than 100, or the rental duration is 5, or let's make it so that we're looking for titles that start with A, and we can use this left function that we learned about in a previous exercise. And we can run that. So what we're doing now is matching on all films where the length is greater than 100, or the rental duration is 5, or the film title starts with the letter A. One thing I haven't touched on so far is regarding formatting. And what I did when writing this where clause was break it out onto multiple lines, rather than have it all on one line. I did that for clarity, because I think it's easier to read in this way. There is actually no standard agreed on convention for formatting SQL statements. The main thing when deciding on what formatting convention to use is just to be consistent throughout your code. There's no one right way to do it. Let's change this last or to an and. Do you know what would happen now if we ran this? Sometimes when you're looking at statements like this, it can be a little bit unclear what order things will happen in. To help clarify your intentions, it's often useful to use parentheses to group expressions together so that it's clear what order things are happening in. So for example, let's group this, and maybe we'll move that onto its own line as well. And now we can run that. And we got 28 rows. So just by adding parentheses, we've actually changed the meaning of what's happening here. We're saying that we want to filter and see films that begin with the letter A and their length is 100 or the rental duration is 5. So these two expressions get grouped together. Only one of them has to be true, and the title has to begin with the letter A. As another example of this, let's change the parentheses again. Let's get rid of from there, get rid of from here, and this time we'll say where the length is greater than 100 or, and we'll break this out onto its own line, or rental duration is 5 and it begins with the letter A. So we were getting 28 rows before. Now let's run this and see how many rows we get. 613. So again, just by adding parentheses, we've changed the meaning of what's happening because we've changed the order of operations and the order that things are evaluated in the where clause. There's also a keyword called not that you can introduce in the where clause. So let's write a query where we're looking at the film table for films that do not have a rental duration of 5. One way we could write this would be to write where not rental duration equals 5. And you can see that that worked successfully. So all of the films in our output do not have a duration of 5. So we were able to introduce the not keyword to flip the evaluation of any expression from true to false or false to true. I find often when using the not keyword, it can be useful to put parentheses around the actual expression. So in this case, we're notting the expression rental duration equals 5. In this video, I'm going to be covering how to deal with null values. Previously, we've touched on the idea that null is used in databases to represent the absence of data or information. As an example, in our database, we have a table called customer, and for each customer, we store their email address. But when a customer doesn't provide us with their email address, that's where we use null to represent that. Null simply says, we don't know what the customer's email address is. Let's pull up our customer table now. If we now wanted to return only those customers that didn't provide us with an email address, so where the email address is null, the way we do that is as follows. We have to write where email is null. And conversely, if we wanted to only return the customers where the email address is not null, we would write email is not null, and we can run that. So we use the keywords is null or is not null to return the rows that we're after. You may be wondering why we can't just use the equals sign. So for example, if we wanted to return customers where the email is null, why couldn't we just write equals null? Let's give it a go. We didn't get any results. What about if we wanted to see where the email address was not null? Let's try the not equals to. That didn't work either. What's happened here is that in SQL, the evaluation of some comparison can actually be either true, false, or unknown. SQL uses something called three-valued logic. When you're doing comparisons that don't involve null, you'll always just get true or false. So if you're working with a column like create date, like the customer table has, which can't be null, the result is always just going to be true or false, and you've got no problems. However, comparing anything with null results in unknown. So when we were just trying now email equals null, and now we were trying email is not equal to null, in both cases the result was unknown. And what's interesting is that a where clause will only ever return rows that evaluate to true. So it won't return rows that evaluate to false, and it won't return rows that evaluate to unknown. What that means is that if you're filtering on a column that could have null values, you have to be extra careful. Let me give you an example of where you have to be careful, looking at the film table. Let's bring up the film table now. And what I'm interested in is the rating column. So let's just change this so we're only returning the title and the rating for each film. I'm working with the rating table, but I know that I actually have to be careful here because I know already that this column could contain nulls. How do I know that? One really easy way you can check if a column could contain null values is to go over to your relationship diagram. And what we want to do is right-click anywhere here in the background, go View Styles, and Show Nullability. And we can see looking at our rating column that it doesn't say not null next to it. So that indicates that this column does accept null values. Incidentally, because null is quite difficult to work with, this is also why if you're designing your own database, you should put not null constraints on columns as much as possible to ensure that null values don't accidentally get inserted where you don't want them to be. Let's go back to the exercise though, and what we want to do is view all films where the rating is not PG. So let's first take a naive attempt at it. Let's say from film where rating is not PG, and we can run that. And we got 804 rows. However, we've now learned that if a film does have a null rating, this check that we're doing, this rating is not equal to PG, would actually evaluate to unknown for that film, and therefore that film would not be returned in our results because it did not evaluate to true. But we actually want that here. We want to know all films where the rating is not PG, and that includes films that don't have a rating. The way we can do that is to update our query to also check if the rating is null. And we can run that, and now we see that we got 807 rows returned. So what that means is that there were 3 films that had a null rating. And now we have a true complete list of all of the films that are not rated PG. Null is quite a tricky concept to deal with. Whenever you're writing queries in the future, you should always be checking if the columns you're working with could contain null values, and if they do, you usually have to do something explicitly to handle that to make sure that your query is still correct. In this video, I'm going to introduce a couple of other keywords that can be useful when you're filtering with where. The first keyword is between, which you can use to check whether a value is in a specified range. So for example, if we're working with the customer table, and if we wanted to only return those customers where the ID is between 1 and 5, we could use the between keyword. Running that. So rather than using greater than or equal to and less than or equal to, we can use between. It's a much simpler, more condensed way to write the same thing. And we can also do not between. So if we only want to see the customers with an ID that's not between 1 and 5, we can just put not at the front, like so. The other convenient keyword that I want to introduce is in. And you can use in to check whether an expression is equal to at least one of the elements in a set. I'll demonstrate this by only returning customers where the customer ID is either 1, 5, or 8. Running that. And we can also use not here as well for the same effect. And so you can see here in the result set, we've returned all the customer IDs except 1, 5, and 8, which are missing. You can also use these keywords to filter expressions as well. If we wanted to write a query which only returned the first names that don't begin with A, F, or J, we could do this as follows. And we'll use this left function that we learned about earlier. And we'll run that. And so what we've got in our output now is only those customer names that begin with A, F, or J. And we've used this left function, as we have in previous exercises as well, to just obtain the first character in a customer's first name. And so in and between are just nice convenience keywords that save us having to chain together lots of logical and/or conditions. A third keyword I want to introduce in this video is the like keyword, and we can use the like keyword to search for patterns inside strings. This is a big complex topic, and Postgres actually has full support as well for rich text regular expression matching. For now though, let's just look at the like keyword, and let's look at two common wildcards and their usage. The first wildcard is the percent symbol. So what I'm going to do is write a query that returns all the customers where their first name starts with M. And I'll use the new like keyword. Running that. And you can see in the output, I've returned all the customers that have a first name that starts with M. So what I've actually done here is specify a pattern which is matched against the customer first names. And what I'm saying is that the first name has to match the pattern of starting with the letter M, and then I use the percent symbol after that. And the percent symbol will match any string of characters, including an empty string. When you're using the like keyword, you can also match just a single character. Let's say then that we wanted to write a query where we wanted to return all the first names where the third character in the name is an M. We would do that like this. __M. And you can see that I got 5 results there. So these are all the customers with a first name that has an M as the third character. I'm actually missing one more thing though. What I should really have here is a percent symbol. And now what I will match finally is customers that have any character appearing as the first 2 characters of their first name. The third character must be an M, and then anything after that is permissible. So let me run that now with this fix. And you can see now I've actually got the output that I wanted. So I match now on customers with the first name like Emma. The like keyword is part of standard ANSI SQL. There's a variation of this which is just specific to Postgres, and that's ILIKE. And what ILIKE will do is it will perform that same type of matching, except it will be case insensitive. So in this case, whether you're matching uppercase M or lowercase m, the results will be the same. So let me change that to a lowercase m now, and you should get the same results. There are some other wildcards that are supported as well, in addition to underscore and the percent symbol. And there are actually some other keywords as well, like similar to, and even full regular expression support. In my opinion though, it's the kind of thing that you should just look up and learn about when you need it. And I've included a link in this video description where you can learn more about string and pattern matching. Just to give you a quick glimpse though, there's another keyword called similar to, which again is part of the ANSI standard, which does actually have pretty good regular expression support. I'm not going to go into detail and explain this a lot, but just to give you a bit of a fun example of the kind of powerful things you can do with similar to and full regex support, what I'm going to do now is show you a query where I'm returning all the customers with a first name that starts with M and contain 2 repeated letter L's somewhere in their name. So I'll do first name, similar to, starting with the letter M, and anything can come after that M. It needs to have two L's repeated, and then anything can come after that. So let me run that. So there are 3 customers with a first name that start with the letter M, and for each of those customers, somewhere in their name, they have 2 repeated L's. So that's just an example of the kinds of fun types of string and pattern matching that you can do with similar to. If you're interested in learning more about different ways that you can match text and all the types of regular expressions you can do with SQL, click the link in the video description and check that out. And as always, make sure you have a good go at the exercises. I think there's some really interesting exercises that accompany this particular video. In this video, I'm going to be introducing the order by clause, which you can use to guarantee the sort order of the output. SQL actually has no guaranteed sort order for when you're writing queries. And what I mean by that is so far when you've been executing queries, Postgres is actually free to return the rows in any order that it wants. The sort order is not guaranteed. If you want your query output to be sorted in a particular order, you need to use the order by clause. Let's start things off by selecting from the film table. And we now want to order the films by their length, so we can use the new order by clause. Running that. And let's scroll through the output to see that it's sorted. Okay, it looks like the films have been sorted by length, and they've been sorted in ascending order. Ascending sort order is the default, so if you just say something like order by length, you're going to get the films sorted in ascending order, so numerically increasing. If you want to explicitly say to sort ascending, you use ask like this, and rerunning that, and you see you get the same output. But that's the default, so you don't have to write that in. You can also sort descending order. And you can see now, if we scroll through the output, that the films have been sorted by their length in descending order. It's interesting to note that there are a couple of films with a null length, and they appeared at the top of the output. In a later video, I'll show you how you can use something called case statements to deal with whether you want nulls to be sorted first or last. And that's the standard way to handle this. There's actually a non-standard way though to specify how you want nulls to be handled. For example, whether you want them to appear first or last in a sorted list. But it's commonly supported by a number of different databases, so I'll show you that here. What you can do is write nulls first, and that will make sure the nulls appear first in the list. If you want the nulls to appear last in the list, you can write nulls last. We can run that, and let's scroll to the bottom of the output, and we can see that those films with a null length now appear at the bottom. You can actually also order by multiple columns, so let me first just return this to ordering by length only, and we'll scroll up to the top of the output. So right now all we're doing is ordering by length, and it's default ascending. What if we wanted to order by length and then by the title of the film? So right now, all the films that have a length of 46 minutes, you can see the titles aren't sorted in any particular order. So they're not alphabetically sorted, for example. If we wanted to, we could sort by length and then by title to correct that. So we put comma, title, and running that. And what you can see now is in the output, films have been sorted first by length, so we're still sorting first by length in ascending order. But if you have more than one film that has the same length, it's now going to get sorted by title. So you can see that the titles now are sorted alphabetically. So Alien Center, Iron Moon, Kauai Homeward, Labyrinth League, Ridgemount Submarine, and so on. That's sorted alphabetically. If we now scroll down a little bit and go to the next length, which is 47, you can see that again, now, starting with length 47, the titles are sorted alphabetically as well. So starting with D, and then H, S, and then again, when we go to the next length, which is 48 minutes, the titles get sorted alphabetically again, A, H, M, N, O. So you can sort by multiple columns if you want. And a good way to read this and to think about it is order by length and then by title. And you could even add more columns, so you could add additional columns here, whatever they may be. Right now we're ordering by length, ascending, because ascending is the default, and then by title, ascending, because again, ascending is the default. However, if you wanted to, you could mix that up, so you could order by length, descending, and then by title, ascending. Let's run that, and let's have a look at the output. So we've sorted by length descending, so the films start at 185 minutes, and then the lengths go down. And within that, we've then sorted by title ascending. So C, C, D, G, H, M, P, that's going up in ascending order, alphabetically. So you can mix and match ascending and descending sorting, even when you're ordering with multiple columns. You can order by expressions as well. Let's imagine that for some reason we wanted to sort all the films by the last character of their title. What we need to do first then is find a way to get the last character of the title. And in earlier videos, you've seen this function that we've used a few times called left, which we've used to get the first character. There's a corresponding function called right, which we can use to get the rightmost character or characters of the title. So let's use that. And we run that, and let's have a look at the output. Okay, so what we can see here is that the titles are now sorted based on the last character. And the default sort order, because we didn't specify anything, is ascending. So going alphabetically up, A, B, C, D, and so on. So let's scroll down the output and let's make sure that's the case. And I'll make this a little bit bigger, ending with B, C, D, E, and so on. So that looks like that worked. So here we're ordering by an expression, not just by a column. And if we wanted to, of course, we could introduce another column to order by. So let's order by length, and let's make that descending. And let's look at our output, and let's make sure that worked. Yep, that appears like that worked. So we first ordered by the last character of the title, and then by the length, descending. You can also order by aliases that you introduced in your select. To demonstrate that, I'm going to paste in a query that we've seen a few times now in the exercises. And I'm going to run that. This is the query where we've introduced a new column alias called break-even, and break-even calculates the number of times a film needs to get rented out to cover its replacement cost. So the break-even for Academy Dinosaur is 22. This film needs to get rented out 22 times to cover its replacement cost. We've seen this query now a couple of times in the different exercises we've been doing. If we want to, we can order by that break-even column. So let's do that. And let's order by descending. Looking at the output, yep, that looks like that worked. You may not think this is very interesting, but there's something that's quite special happening here. For example, we're referring for the first time to a column alias that we introduced in our select statement. You may or may not have tried previously, but you actually can't do that in some other places. For example, let's try and refer to this break-even column in our where clause. Let's say where break-even is greater than 20, and we'll try and run that. We get an error. It says the column break-even does not exist. So that's quite interesting. Why does break-even exist when we're in our order by clause? Why can we refer to it there? Why can't we refer to break-even in our where clause? I'll explain what's going on in the next video.